So previous class we have discussed the galvanic cells, and also we have discussed salt bridge and the conditions of salt bridge and the functions of salt bridge. So today class we will discuss the topic is electrode potential. Electrode potential. So if I draw a if I draw and if I take a metal here and any electrode rods, and let me take any electrolytes. So this is electrode rods, we have already discussed since from past class. This is electrode rods and this is electrolytes. So if I take electrode rods, any metals, and I have to take the same metal ions, whatever the metal I take, of that same metal ions I will take. If I take metal is zinc, then I will take metal ions as zinc 2 plus, that is ZnSO4, this one. Okay, so I will write, if I take metal as zinc, then metal ions I will take ZnSO4. This ZnSO4 means Zn2 plus. Yes, because Zn2 plus and SO2 minus exists, so this is taken as Zn2 plus. So if I take any metals, then I will take the metal ions of the same metal. Why? Because if I take other metal ions, then that oxidation or reductions occurs, and the redox reaction occurs, means at the same beaker both oxidation and reductions will happen, and due to this huge amount of heat will be released, and that we can't use it, that will be wasted. So for that reasons we will take same metals and the same metal ions, so that the generating heat we can use by taking two beakers and two electrolytes in different cells of having same metals and same metal ions in both the beakers. Okay, but if you take the same beaker with different metal ions, then what will happen? Both oxidation and reductions will happen, and due to this heat will be released and we can't use that one, so we will take differently. Okay, that things we already discussed in galvanic cells. So today our topic is electrode rod. So I take one beaker, I take electrolytes and electrode rods. Electrode rod I take metals, and the electrolytes, that is metal ion, I will take Mn2 plus, means this. If I take zinc, then I have to take zinc sulfate solutions, and if I take copper, then I have to take copper sulfate solutions, means same metal and same metal ions I will take. Okay, so metal H, generally metal H tendency to lose electrons. So here the metal but it lost electrons. So whenever this metal lost electrons, what happened? I am drawing another little bit bigger picture. So let's say whenever here is solutions, let's say any solution, whenever this metal loss electrons, means whenever this loss, this is the metal, so this metal loss electron, this is metal, so whenever this metal loss electron and it convert into ions, so this metal is converting into ions after losing this, giving electrons. So in the galvanic cells we have discussed that whenever the metal is losing electron, this electron is going into the electrode rods, that's why this electrode rods get a negative charge, we have discussed. in galvanic cells. So this electrodes getting negative charge, and this metal is coming into the solutions, and the solutions is getting positive charge. So we have discussed that whenever we not apply the salt bridge, then that electrodes getting negative charge and the solutions getting positive charge. So due to this, what happened, let's say this is metal rods and the solutions. So these metals, whenever this metal getting oxidized, so this give leaving electrons into the electrode rod. So this rod is getting negative charge, and whenever this metal coming into the solutions, so extra positive charge is coming into the solutions, means this solution is getting positive charge. So this solution is getting positive charge, positive charge. And what is happening here, that one side is negative charge, other side is positive charge, means negative charge is surrounded by positive charge, means in between this one potential difference has developed. So whenever there is a charge separation, there will be a development of potential difference. So here the charge separations has developed because this negative charge and positive charge. So due to this, the charge here is positive, here negative. So charge separation has developed. So if charge separation has developed, then here the potential difference will be generated. The potential difference will be developed. So here charge separation is there, so potential difference is developed. So here potential difference is developed. And what we know that if metal the difference, the potential difference between metal and metal ion at equilibrium is called electrode potential. So what happened here, so this is electrode rods or this is metal rods. So this metal rods getting oxidized means it is giving electrons to these electrodes, and the solutions getting negative charge, positive charge. So here this is actually due to metal. So here assume that this metal is leaving electron, right? So this is metal. So due to this metal and the metal ions, there is a potential difference. So what is said that the potential difference between metal and metal ions at equilibrium is called the electrode potential. So what it actually means, so here this metal, what due to this is a tendency to lose electron. So this loss electrons, and electrons is here in the electrodes we have in the galvanic cells we have discussed, whenever the metal oxidize, it leave the electrons in the electrodes. That's why the electrodes was getting negative charge. So this metal leave electrons here, and in the solutions, due to metal is coming into the solution, so metal ions more positive charge is, means this solution is getting positive charge, because metal ions metal positive charge is coming into the solutions, means extra positive charge is coming into the solutions. Previously this was both positive and negative charge was in a neutral form, but whenever the extra positive charge is coming into the solution, so this ions get positive charge. So this ions with positive charge and this electrode due to negative charge, there is a potential difference. So what it says that the potential difference between metal and metal ions at equilibrium. At equilibrium means at that situation where no more metal can oxidize. Means let's say this is metal oxidized to metal and plus and electron. So T equal to 0, let's say C concentration of metal is there 0 0, T equal to T equilibrium. So let's C alpha, C minus C alpha. So this is the equilibrium conditions. At these conditions, no more metal will oxidize to metal and plus. Means this is the stable pump. So at these pumps, how much metals oxidized? Means at this pump, how much metal oxidized? So that metal charge difference has created between metal and metal ions. So on that stage, the potential difference between metal and metal ions is called electrode potential. Means the stable form. Yes, we already discussed that T equilibrium means that stage where no more metals will ionize or no more metals will oxidize. So at that time, how many positive charge and negative charge is there in electrode and metal ions, and due to that potential difference has created. So that potential difference is called potential electrode potential. Okay. So next we will discuss that factors affecting electrode potential. What are the factors that affect electrode potential? First is nature of metal and metal ions. Let's say if I say Fe, and if it is oxidized to this and same metal, let's say Fe3 plus 3 electrons. So this metal and this metal, the nature will be different. Since, and if I say and Zn, and so these all will be differ. So this nature of metals will be differ. So the nature of the electrode potential will differ for both three cases. So first depend on the nature of metal and metal ions, and secondly it depends on partial pressure of gas or concentration, and third factor is temperature. Okay, so these are the three factors that electrode potential depends. First is nature of metal or metal ions, and then second one is partial pressure or concentrations, and third factor is temperature. So these factors it depends. So if I say that what are the standard electrode potential? Standard electrode potential. So standard electrode potential means this electrode potential depend on these three factors. Means if these factors, if we become some standard condition, say at two standard conditions electrode potential is called as standard electrode potential. So what are the standard conditions? First is the same things that affect potential partial pressure and gas and temperature and concentration. So the concentration has to be 1 molar. And second factors is, and second standard condition is temperature has to be 298 Kelvin. If the reaction is happening at 298 Kelvin, then only we called it as a standard electrode potential. And third is the partial pressure. The partial pressure of gas has to be 1 atm. So if it satisfies these three factors, then we call it standard electrode potential. Okay. So let's say here if I take two beakers, I have discussed in the galvanic cells. We already discussed. Let's say I take an electrodes, any electrodes I take, and electrolytes I will take. Let's say I take any electrolytes. And I connect this to one bulb so that I can understand that current is produced or not, and I will connect one short bridge. YouTube short bridge. Let's say here KCL is there. So here this is here anode and this is cathode. So this anode means oxidations, and cathode means reductions, and here loss of electrons, here gain of electrons, and let's say metal will gain loss electrons, and here metal will gain electrons. So if I write this in terms of electrode potential, then what? So electrode potential is represented by E. So this one in electrode potential terms, how I represent E? So from M to Mn plus. Okay. Similarly, this is represented by E Mn plus then M. Okay. This is the representations of electrode potential. So this is the representation for oxidation and for reduction. For oxidation, the representation of electrode potential is this, and for reductions, and the electrode potential representation will be like this. And at standard conditions, it means at 298 kelvins and concentration equal to 1 molar and temperature is and partial pressure is 1 atm, then it is represented as E. Similarly, this is E naught M, that is T equal to 298 Kelvin and partial pressure is 1 atm and molar is, or you can write concentration is 1 molar. So the another terms came, that is EMF of the cell. EMF of cell. What do we mean by EMF of cell? Means we have did one is anode, another is cathode. So the potential difference created at anode is called oxidation electrode potential, and the potential difference created at cathode we call that reduction potential. So the potential difference created at anode or at the anode electrode rod, that is called oxidation potential, and similarly the electron potential difference created at the cathode rod, that is called reduction potential, that is represented by this. This one we call as reduction potential, this is called as oxidation potential, this is called as reduction potential. This is oxidation potential, this is the reduction potential. So in galvanic cells, the cell is working due to both because are working continuously, simultaneously. That's why you use the salt bridge, and after that only this circuit is complete, and the circuit is complete and the bulb is glow and we able to produce electricity. So now the question is, what is the EMF of the cell? EMF of the cell means the electrode potential, the difference of two electrode potential cells. So this electrode potential cell is oxidation electrode potential, and the electron potential is reduction potential. So the difference between the electrode potential of these two cells is called the EMF of the cell. EMF of the cell means the potential difference, or sorry, not the difference of electrode potential between two electrode rods. This means in this one rod, let's say that is for anode, the electrode potential is anode, the electrode potential is oxidation potential, and another rod, that is cathode, and for that electrode potential is reduction potential. So the difference of electrode potential between two electrodes, one electrode is oxidation potential and that is for reduction potential. The difference between these two electrode rods in terms of electrode potential, that is called EMF of the cell. So EMF of the cell means the difference of electrode potential of, we can write of the difference of electrode potential of two electrode rods. Okay. So what I said, that EMF of cell is equal to E electrode potential of oxidations plus electron potential of reductions. So this one also I can write, or I can write E of anode plus E of cathode and now we have to discuss little bit about SRP series. So not SRP, now we have to discuss little bit about IUPAC nomenclature. Why? Because in IUPAC, what is said, this is the standard things which everybody has to follow. So what they used to take that they standard or electrode potentials, they take that electrode potential they will talk in terms of reduction potential only. So they take that electrode potential only in the reduction potentials, and oxidation potential they not take. So for that what you have to do? So they only take the reduction potential, they not take the oxidation potential. So for that case we know that reduction potential is equal to minus of oxidation potential. It means if you have the electrode potential equal to reduction potential, this is taken by the IUPAC. So IUPAC only take reduction potential, they not take oxidation potential. But we know that reduction potential is negative of oxidation potential. So I will just put this electrode potential equal to reduction potential equal to minus of oxidation potential, because the reduction potential equal to minus of oxidation potential. Okay, so here what we have, E anode upon E cathode, this is for oxidation potential, this is of reduction potential, but we will not take oxidation potential in IUPAC. So I will write below. So EMF of cell, that is this is E anode plus E cathode, this is oxidation potential, this is reduction potential. So since in IUPAC we will not take oxidation potential, but we know that oxidation potential equal to negative of reduction potential. So what I do, EMF of cell, so instead of oxidation potential I will write minus of reduction potential. So that is, I will write E of anode. So E of anode, I will write reduction potential, I will write E of anode. So for minus I have to put minus. Okay, and this is again this is already in reduction potential, so this is positive. E cathode, this is in reduction potential, this is also in reduction potential. So in IUPAC everybody know that they only take reduction potential, so it is simply written as EMF cell equal to minus E of anode plus E of cathode, because that it always take in reduction potential, so they will not write, they simply write like this. So this also can be written as EM of cell equal to E of cathode, E of cathode minus E of anode. And this cathode is in which side? Cathode is in left sides and the anode is in right sides. So this also they can write that EMF cell, EMF also can be written as E cell. E cell equal to E of, so cathode is in right, left side, left, E of right. That is written as E cell equal to cathode is in which sides? right side, so E of right minus E of left. This also they can write. So you know that for standard conditions we will write at temperature equal to 298 Kelvin, pressure equal to 1 atm, and concentration equal to 1 molar. Then E is taken as E naught. So a standard condition we can write E naught of cell equal to E naught of right minus E naught of left. Same case, E of naught of cell equal to, we can write E naught of cathode, E naught of cathode minus E naught of anode. Okay, so today up to this, next class we will discuss more. Thank you.